The next speaker is a colleague who works in the Department of Pesticide Regulation. His name is Robert Budd. He has a master's degree from University of Colorado and got his PhD from UC Riverside, but he's more importantly been a really strong partner on working on urban pesticides with us, including Rich and Robert and Noel from the Division of Water Quality are sort of charging ahead on this really exciting project under our stormwater strategy effort. So with that, thank you for coming and speaking, Robert.
Great. Thank you for inviting me here to speak today. It's a pleasure. Today I'll be giving just a basic overview of the Department of Pesticide Regulation Surface Water Monitoring Program. I specifically work in oh, sorry. This was turned this way. Can you hear me now? Okay. So this is a bubble graph that represents a general overview of our all the components within our program. And all of these aspects work together to achieve our primary driver, which is to protect the surface water quality. Now today I'll be focusing on the green bubble here of our monitoring portion. And the data that we generate in our monitoring program helps feed and answer questions in all of these other aspects, including mitigation, modeling, assessment, outreach, regulation, and prevention. Our primary monitoring objectives is first and foremost to determine what pesticides are present in California's surface waters and if the concentrations are reaching levels that are potentially toxic to aquatic species. We use our use reports that are reported in our PUR database and compare that with our monitoring data to help us identify sources of contamination. And the data also allows us to evaluate both spatial and temporal trends in concentrations. So currently in California, we have over 1,000 active ingredients registered. So obviously this is a massive, massive task to monitor. We can't monitor for all of these. Some of my favorites include dried blood and coyote urine. I don't know who is harnessing these for pesticide use, but I would not volunteer for that job. So to help us identify what the most important pesticides for us to monitor, we've created a online tool, which is a monitoring prioritization tool, which is based on current use and toxicity data, as well as physiochemical properties. And what, sorry, you can't read any of this information, but the tool allows us to delve into specific spatial scales, like what we recently added a watershed tool, as well as county, and you can also do by month data and specific crop or use patterns such as structural or landscape uses. This is an output from our prioritization model. There's two different outputs, one for the statewide urban prioritization list and one for the agricultural landscape. So what the model does is generates a use score or toxicity score for each associated chemical, and then the product of these two values gives us a final score. So this is a little blurry. And then it helps rank those values to give us an importance of each active ingredient. Finally, based on the physiochemical properties, the model generates a recommendation whether to model or not. A true meaning that it recommends to monitor, and a false recommends it not being monitored. So our monitoring program is broken out into the urban and the agricultural landscapes, as I mentioned. First, I'll be delving into the urban section. This represents, the red circles here represent the watersheds in which we sample throughout California. We sample at both storm drains underneath residential areas and larger downstream receiving waters. Currently, we're monitoring at 12 sites in Northern California and 15 sites in Southern California. We've stayed pretty consistent with our sampling protocol since the development of our program in 2008. We currently sample 4 to 5 events per year, approximately half during the dry season and half during rain events. We try to get the first flush because we know that that's an important component for contaminant transport. As I mentioned, the sites are located either at storm drains directly below residential areas or at larger receiving waters. Currently, we're monitoring for approximately 35 active ingredients, and wherever possible, we're measuring both water quality and flow measurements for each of our sampling events. So the next couple slides are going to be representations of how we use our data to answer specific questions. They're all going to be set up the same with the pesticides of concern along the x-axis and the detection frequency along the y-axis. So this data represents all of our sampling, urban sampling between 2009 and 2016 statewide, with the orange bars representing the detection frequency of the chemical, and then the red bar, the percentage of those detections with concentrations above a toxicity, exceeding a toxicity threshold. And the toxicity threshold that we typically use at DPR is the minimum aquatic benchmark set by the US EPA. And as you can see, the majority of the exceedances are represented by the class of chemicals of pyrethroids, with bifenthrin being far and away the most frequently detected chemical and with associated exceedance values. But I think Brian mentioned that we do detect imidacloprid, I would point out, at fairly high high detection frequencies in the urban environment, as well as fipronil and some herbicides. This is that same data set broken out by region, and the red bars indicate that we're detecting most of the chemicals, with a few herbicide exceptions, more frequently at our Southern California sites compared to our Northern California sites. And this is mostly due to difference in pest pressures, which results in different use patterns down there. We are also very interested in the effects of stormwater and what the effect that has on the transport of contaminants. And as you can see from this is the same site, a picture, and what a dramatic effect between the dry season and the rain events on water quality. This is that data set broken out by season during the dry season in orange and the red representing the stormwater runoff. And almost every single chemical is detected more frequently during the stormwater events. And a lot of the pyrethroids and fipronil down in Southern California are almost detected every time we go out and sample. Lastly, another way to look at the data is by the hydrology. As I mentioned, we are looking at, we monitor at storm drains to help us identify the primary source identification of the chemicals. But we also are interested in the downstream receiving waters. And so we break out the data to help us evaluate any dilution effects that may occur once it's left the storm drain. So as you can see, we do detect chemicals more frequently at the source, at storm drains, but I would highlight that we're still detecting most of our pesticides at similar frequencies downstream in our receiving waters. We do collect and conduct toxicity tests on a subset of our samples. And these tests are conducted on Hyalella azteca, which is an amphipod, which is very, very sensitive to pyrethroid insecticides. So this is a summary of all of our toxicity data collected at storm drains over here on the left and downstream receiving waters during the dry season and storm events. So obviously from this graph, you can tell that waters collected at storm drains during storm events are much, much more toxic than waters collected during the dry season at receiving waters, which is what we would expect. Now, unlike that Brian talked about the SPOT program, we do a subset of a very, very subset of our samples. We collect sediment samples and analyze for toxicity data, or I'm sorry, for pyrethroid concentrations. And from those pyrethroid concentrations, we can calculate an estimated toxicity through what's called a toxicity unit, which is the organic carbon normalized concentration divided by its associated LC50 value. So anytime we calculate a value greater than 1 is what we estimate a potential toxicity. And so for all the samples that we've collected in the urban environment, we pretty much expect a toxic response. So when you look at contributions from the individual chemicals for the toxic units, we see far and away bifenthrin is the largest contributor of TUs to our system, followed by cyfluthrin and cypermethrin. Now I'm going to switch gears and talk a little bit about our agricultural monitoring program. So the green circles here represent the spatial distribution of our sampling sites throughout California. Currently, we're monitoring 8 sites in Northern California and 16 in Southern California. And they monitor at both agricultural drains and downstream receiving waters. The sampling design for the agricultural monitoring is a little bit different from the urban, in which they look primarily during the growing season. They focus at many more events per year, but they're currently analyzing fewer analytes than our urban monitoring. And they also record water quality and flow as well. So this is a similar display of all the detections within the agricultural monitoring from 2011 to 2015. And again, it looks drastically different from our urban monitoring in which the chemicals of concern are quite a bit different. In the ag setting, imidacloprid is the biggest, the highest detected chemical, but we also do see quite a few pyrethroids still with exceedances over that benchmark value. And that's primarily driven by the very low benchmark values for pyrethroids. So all of our monitoring data is stored within our surface water database, or SURF. So currently, we have records going back to 1986 with records given to us by over 25 agencies representing 54 counties within California, 1,500 individual sites, almost 500,000 records for water samples, and 72,000 sediment records. And I'll also highlight that all of the information is publicly available through this website right here. It's their Google Fusion table interface. And if you probably aren't writing this all down, but if you are interested, we can get to that to you very easily. We also utilize our monitoring data to help evaluate the efficacy of specific BMPs or best management practices, including water quality ponds, constructed wetlands, and vegetated buffer strips. And we typically sample at the inlets and the outlets of the treatment area to evaluate the efficacy. And lastly, if the mitigation fails, we do have several regulatory actions at our disposal, including the surface water regulations that affect pyrethroids sprayed on structural applications that went into effect in 2012. We can classify a pesticide as a restricted use chemical, such as the chlorpyrifos that was recently implemented in agricultural settings. Or finally, we can cancel a product such as carbofuran. And that is it. So I would like to just thank our team for following me down into the storm drains late at night during rain events to generate this great data set.
I'm wondering if you take a look at other data besides water data in terms of the regulatory action that DPR can take. And for example, I'm talking about the drift catcher, which is showing longer term exposures to drift. I don't know if you're familiar with the Pesticide Action Network of North America's drift catcher, but I understand it's being used in certain agricultural communities, and it's showing a volatilization of the chemical off the crop for up to a 72-hour period. And I heard that that was being used in review of product registration. But it's another source of data that's out there about pesticide levels.
So you're asking, just to clarify the question, you're asking more about what data goes into product registration? Is that?
Product review. I mean, I know you didn't really talk about that. You're really
Right.
You're talking about water quality
Right,
data, but because you mentioned that there are that you have a regulatory framework in which to cancel products or create some sort of restrictions, just wondering if you're also using air quality data.
Sure. So that's a different program, but I will say that the product registration process involves all groups. So that any new product that would potentially affect surface water or surface water runoff would come to us for review, and we have a model, a runoff model that will help us predict concentrations based on the use pattern that is given to us, and then we will that model will help us evaluate the potential threat to surface waters and give a recommendation either for recommending for registration or not. But
Well, as a follow-up to that, then how do we get to the point where pyrethroids are being found in so many downstream waters and after they've been registered and used for years?
how do we get to this point? Well, they first of all, we're an evolving program, and so we didn't have the model at the time of pyrethroid registration. They've been registered for how long? Long time. And so, we're playing a little bit of a catch up, but this should drastically affect how we move forward to help prevent new chemicals from coming on the market. I think Brian mentioned the treadmill that we've been on, but this will help us going forward to help prevent that from happening again. And we are addressing the pyrethroid issue.
I'm wondering if you guys are also doing your testing for the mitigation methods, or if you're adopting existing mitigation methods that are already proven to work for specific pesticides.
I'm not
Let,
sure if
let me try to clarify.
yeah.
There are new techniques and innovations coming through in terms of mitigation techniques. Do you have a protocol to test those techniques to see which
Oh,
one works best for specific pesticides, or do you depend on what's been proven to work in the field and just adopt those?
right. So we aren't a research facility or an organization per se. So what we tend to do is work with our collaborators to help test the new techniques that are coming on the market. So we help fund several contracts, and then we will take that data and help us evaluate the practice. So it's usually specific to a specific chemical.
I see. So academic research mostly.
Yes,
Okay.
yes. So we don't do the research per se in-house.
Thank you.
Right. Do you have a mechanism to accept data from others? Like, so there's a lot of other data that gets collected on a lot of these compounds, in both storm drains and receiving water. So do you have a protocol or method where you can receive data from other programs that are collecting that might be helpful?
Yeah, data sharing is a big topic right now. So I don't know if it's been mentioned in any other talk, but there's also the water board that has CEDN, which is a very large data set. And we're working to collaborate to integrate data from both those. So there's more of an open highway between. So we have a database administrator on our end that has been taking data from CEDN specifically for pesticides and pulling it into SURF. So the slide that I showed, that's not all data that, like I said, it represents data from 25 agencies and thousands of sites. So that's not all of our data. That's data that's been collected by numerous programs.
Hello. I had a question about the score that's generated that triggers monitoring. Could you briefly explain some of the factors that are considered as that score is developed?
Yeah, so the prioritization model is based on, so there's two primary factors. There's the current use. So all the pesticide use professionally applied gets uploaded into our PUR system. So we do a 3-year average for the chemical. And now these are just the default. So the user can actually specify different parameters. But the default is a 3-year average. And then that will give a percentile ranking. And so we'll have numbers 1 through 5, 5 being the highest used chemical in whatever setting. Then we'll have a toxicity guideline, which is based on benchmarks or an associated toxicity value if those aren't available. And those will also rank those 1 through 7. And then the product of those two gives us a
What goes into the selection of the sampling sites, especially for urban areas? And how often does it change? Does it account, for example, for if you're sampling an old built-out watershed versus if you're sampling an area that's being newly developed with all the implementation measures, from the MS4 permits going into it, where you would probably get better data? Thank you. That's all.
yeah, that's a loaded question. But it's very important. So we have been an evolving program since 2008. So when I first joined the program, we sort of took over sites that were previously monitored. We had a specific task of looking at runoff generated from residential areas, so it was from a larger study, and it looked at specifically from single family homes. And from that, we've expanded out to larger watersheds. So now we're looking at much larger watersheds. So in terms of, there's always a compromise, right? So we've kept a lot of the sites the same since the inception of the program because we want long-term monitoring. You know, you have to go, we're only going 4 times a year, so we want a consistent place that we can look at how the trends are doing over time. But in essence, though, we've also expanded out to a lot larger. Now we're looking at like the LA River and the Bouquet Creek, and a lot of the sites that Spot and Brian's group has been looking at, we've taken their data and looked at where the hot spots are. We're really target to try to address the most contaminated spots in the state are.
Yeah, I'm interested to know whether you check the persistence out of the pesticide residues that you have identified. What is the level of the persistence in the environment and the half-lives?
Persistence? I'm sorry, can I just clarify that you're asking about the persistence of the chemical?
Of the out of the major pesticide residues that you identified, can you give a summary of their persistence in the environment in terms of half-lives?
Yeah, the metabolites are definitely an issue, but it's very, I mean, to give you a general answer is very specific to the chemical. Some of them break down almost instantaneous and some of them persist. So the pyrethroids, for example, are extremely stable. And that's one of the major issues with the chemicals in general is that once they're there, they're sticking around, they're sorbing to the sediment so strongly, they're sticking around for years. The other, I didn't talk about another major active ingredient as much, which is fipronil, but on my graphs you might have seen there's several degradates of fipronil that they're just as toxic and persist longer than the parent compound.